It gives me great pleasure to introduce the keynote speaker today, Tal Rabin. Tal Rabin is the head of research and research fellow at the Algorand Foundation. Until recently, she was the manager and research staff member of the crypto research group at IBM TJ Watson Research Center. For many cryptographers, interning in her group under her mentorship was an important part of our PhD process in cryptography. Her research spans a wide spectrum within cryptography. A few that have inspired, influenced my research include secure multi-party computation, threshold cryptography, and composition. And she's done many, many more works in crypto. Tal has served as the program chair, general chair, editorial boards in leading cryptography conferences and journals. She's a member of the SIGACT executive board, serves as a council member of the Computing Community Consortium, and is on the membership committee of the Association of Women in Mathematics. Tal initiated and organizes the Women in Theory workshop. Among many of her accolades, Tal won the Anita Borg Women of Vision Award in 2014 and the RSA Award for Excellence in Mathematics in 2019. She's a fellow of the IACR, American Academy of Arts and Sciences, and ACM. She was named America's top 50 women in tech by Forbes in 2018. Without much ado, I would like to welcome Tal, and I'm going to clap on everyone's behalf.
Tal, you're muted.
Yeah, you unmute, yeah.
I'm getting there, one sec. Okay. Do you guys see the slides?
Yes, we do.
But they haven't gone, okay, now they've gone into presentation mode. I must say that this situation of talking to a computer all alone, despite having spent most of my past 7 months in this media, is still a little bit unnerving, but I hope it'll be okay. I looked a little bit on the people, at the people who are at the talk, and I saw one of my co-authors, Ran Tomer, but this is work with many others. You can see the names of people who have collaborated on this work. Okay, so let's start. First of all, this is a workshop that works on standardizing zero knowledge, and specifically ZK snarks is one example. And what's the end? The end is for non-interactive. I have to say that my talk is more about an application of zero knowledge rather than new designs of zero knowledge or anything like that. But I think that this is somewhere where zero knowledge is at this point. It's not that we're reinventing a lot of very, very special things. The ZK snarks, of course, yes, but we're working a lot on optimizing and really using it in things and utilizing it. So this really is a talk about an application of zero knowledge more than specifically about zero knowledge. Okay, so searching for the non-interactive, this started with Blum, Feldman, and Micali when they wanted to do non-interactive zero knowledge. In fact, that was the first instance that we saw it. And for multi-party computations, the path has been a little different because, in fact, it's a very difficult question and there exist lower bounds. And it started with the work of Feige, Killian, and Naor in '94, and then with the work of Levy, Lindell, and Pincus in 2001 that also described the lower bound, which this talk will be about. And then I think really only in 2014 in the paper of Baimel et al. Was it really understood what non-interactive multi-party computation meant, gave the good definition, and put order in this area. However, still things are difficult and solutions have not been coming rapidly on this front, though there's a lot of very interesting work. And of course, today, our reality of 2020, very non-interactive. Okay, so what is multi-party party computations, we have a set of parties, P1 up to P6, for example, and they each have an input. And what you want to do is you want to compute some function of this input, f of x1 up to x6. And how is this done? Basically, the parties interact amongst themselves and they compute the function. Of course, there's a very trivial solution, which basically is everybody announces what their input is, and then we can compute the function. But there are a lot of additional requirements on the output of the function, namely that it would remain, that the inputs of the party would remain hidden as much as possible, that is not exposed by the output of the function. So for example, if you're computing the sum and you know that the sum is 7, let's say you're over the positive integers, you know that nobody had an input more than 7. But you try to restrict the amount of information that is learned. And there are many solutions out there. Most of them are interactive. As I said, non-interactive is sort of more of emerging and struggling area. But it requires also the parties to be available all the time online to communicate and so on. So what would be non-interactive multi-party computation? For people who know what non-interactive zero knowledge is, they can sort of maybe deduce what a non-interactive MPC would be. But the idea again is we have these 6 parties who have their inputs, and we'd want each one to announce a message, but only one message that would go into the world, maybe put on a bulletin board or something, and then that they'd be able to compute the function, f of x1 up to xn. And of course, there are a lot of advantages to this thing, because anything that's non-interactive is more efficient in some sense, not in some sense, in the rounds of communication, it is clearly more efficient. And you want to save on rounds of communication, same way that you want to save in zero knowledge. But more than that, there are also applications where that's the only viable solution. If you want to do voting, you don't want me to need to talk to Daniel, to talk to Muthu, and so on. We want each person to come, to put their vote, and then to go home, and for the result of the vote to be made public. And also, not just for the applications, but even if it's not this type of application, to require that everybody is together at the same time and so on is too much of a burden on the system. If it's a few parties doing the computation, of course it's relevant, but for any computation that's supposed to be for many people, that's not relevant. Okay. So what was the impossibility result that was defined in Highlevel in Del Pincas? Again, what was our scenario? We had P1 up to P6, and everybody just put out a message. And then there is some party, or maybe each one of the party, or maybe a combiner party, doesn't matter what, can calculate the output. But what's the problem? Think about this situation. Because the computation needs to be non-interactive, that's what we want. Assume a setting where P4 is faulty, okay? At the beginning, the first message that he put out was based on his input X4. And then everybody could compute the function. But what can P4 himself do? In his head, all he needs to do is to think of another message that relates to X prime for his input, X prime, X4 prime. Think about that one. And now in his head, this party, P4, can in fact compute the value of a function on another set of inputs, meaning an x1, x3 as before, substitute x4 for x4 prime, and x5, x6. And this is what was defined to be the residual function. And the lower bound states that in all settings, the residual function will leak. You have no way to defend against this leakage because in fact, due to the non-interactivity, the party can in his head do anything. And I gave an example of one party. Of course, if the adversary controls P1 and P4, he can compute the function on all the inputs of the honest parties while checking for all the possible inputs of the faulty parties. So this is a lower bound that cannot be overcome in our model of computation. Furthermore, it is known that these solutions also require to have some pre-shared correlated randomness or some dedicated party that's available throughout the computation to communicate with each party that comes. So this is the setting that we know of what is going on with respect to doing non-interactive MPC. We both have a lower bound that there's going to be a leakage of the residual function, and that the solution requires some pre-shared information or a party that is online. Okay. Now let's move to the blockchain world and see how that world merged with the MPC world the minute that Bitcoin came about. So it was obvious that, and I split the history of what had happened in the marriage between blockchain and MPC into 3 generations. The first generation was simply the use of the blockchain as a broadcast mechanism. Many of the papers that were designed for multi-party computations always make this clean assumption that a broadcast channel exists. How to implement this broadcast channel, what the requirements for it are, and so on, that is never discussed, but it's just assumed. But in fact, the blockchain is a broadcast channel and provides all the needed features for the multi-party computations and has in fact been incorporated to deliver multi-party computations with the utilized broadcast. The second generation was a nice development that people saw that you can take that payment mechanism, which is built into the cryptocurrency system, and incorporate that into the blockchain, into the MPC protocols as well. And this enables to go beyond lower bounds as well of fairness. I'll talk about this a little bit more in the next slide. And then our work, which is Gen 3, did the last step and came to utilize also the miners that exist in this ecosystem to deliver results for multi-party computation and to go beyond the lower bound of the leakage of the residual function. Okay, so let's talk a little bit about Gen 2. So what was the idea? The idea was that, let's say Bob wants to have, in the spirit of the times, he's wearing a mask, of course, he wants to have some multi-party computation be carried out. And what he does, and we're talking here about the two-party because the lower bound for fairness relates to two parties. Let me just say what it is. The lower bound for for fairness in the two-party case says that any party, once it knows the output, can stop communicating and by that prevent the other party from learning the output. And that's not fair. And the question was, how do you get around this? So how did the use of the payment function inside the blockchain was used in order to go over this thing? Bob, who wants to carry out this computation, puts out some collateral and commits to it within the blockchain. And then this gives him an incentive to complete the computation. Why? He can reveal fx1, x2, and then he can retrieve the collateral. Okay? And in instances which they describe in their papers, this collateral is set in such a way that incentivizes Bob to actually reveal fx1, x2. But not always, in fact. Sometimes he might want to walk away. And in that case, forgo the collateral will go to Alice. But the reason that he does this is because keeping the value of the function secret is more important to him than the value of the money. So he's willing to say, okay, never mind the money. I will give up on the secret. But he does have the potential to keep the secret, the output of the function secret. Okay. So now we move to our case, to Gen 3, which is Gage MPC. Gage, by the way, is an archaic word, which in fact means collateral. So it really is a collateral MPC. It was very difficult coming up with a name for this primitive. It may be still isn't a good name. Maybe it will change in the future, but this is where we were when we submitted the paper. So for now, it's Gage MPC. So the idea here is the same. Bob puts down the collateral. It gives him incentive to complete the computation and to reveal fx1, x2. And to retrieve his collateral, he can do that. But on the other hand, if he does not participate and he wants to walk away, he can forgo the collateral. But in this case, the computation will be moved to miners who will actually complete the computation, and there's no way to escape from exposing fx1, f of x1, x2. Okay. And it enables us to go beyond the leakage lower bound under some assumptions. And let me explain what the assumptions are and why does it prevent the leakage of the lower bound. Okay. So first we have to discuss how much should the collateral be? How much money should Bob put down in order to ensure that people will want to do the work, and on the other hand, that the value of the function will not be exposed on more than one evaluation point, right? This is what we want to try and prevent, that the adversary can compute the function, as I said before, or let's say with two parties on fx1, x2 prime, that it doesn't learn the output of the function on yet another additional input point. So what could prevent the adversary from doing it? And now you have to think about the miners and how they compute, for example, the hashes for the blocks in Bitcoin. If the computation to compute another hash takes a long time because there's a lot of bits that are missing, not many people would want to engage in this computation, right? Including the adversary. Maybe not only that it doesn't want to engage, it doesn't have the computing power in order to do this, or the money to pay somebody to do this. So the collateral needs to find a sweet point where the person, Bob, setting out the computation, is willing to put it up as collateral. And of course, that fixes exactly the work, so the miners will always be willing to work for that amount of collateral to expose the function on one point. But Bob has to be sure that the adversary cannot invest that much money in order to compute an additional point on the evaluation point of the function. Let's say x1, x2 prime. So you have to find this spot. But observe a very important point relating to this collateral. For Bob, who sets up the computation, he doesn't really need to spend this money. He can come at the end and participate in the computation of the function and retrieve the collateral. So in fact, he can go very high in how much he sets the collateral. However, for the adversary, this is actually the cost that it's going to take to compute another evaluation point. Okay, let me say this again. The idea is that Bob, who wants the function computed, wants it computed only on a single point. The adversary's goal would be to compute the function on a second point. The computation, the cost of the computation that Bob assigns to this function can be set as high as Bob wants, because, and he has to put money to ensure that that will be computed, because you want the miners to participate. But he can go very high because Bob can always retrieve the money. However, the adversary is actually going to need to spend this money to compute the function on an additional point. This is the computation that leaks the residual function. So we need to set it in such a way that the adversary will not be able or will not want to invest so much money into computing the function on an additional point. Okay. But definitely, if Bob set the collateral at $1 million, Bob set the collateral at $1 million, and the adversary spends $1 million, for sure, the adversary will learn the function computed on an additional point. But how did we break the lower bound? Because we set up the system that as long as it spends considerably less, it will learn no additional information about the computation. Okay, so as I said, the honest party who puts down the collateral can put it as high as it wants, because it can always come and retrieve the collateral when the computation of the function is supposed to take place. We gave that option. But as I said, for the adversary, the collateral is the actual amount that it's going to take it to compute the function. So now we come and we introduce a new assumption. It's a different assumption than things that we have known before, but it enables us to break the lower bound. So it looks like it's an interesting assumption that maybe we can do even more things than just to do this thing here. And the assumption says that an honest party can always put down a high collateral higher than what the adversary can actually expend on computation. And as long as this assumption holds true, we can achieve nice things. In our particular case, we can achieve non-interactive multi-party computation that goes beyond the lower bound of exposing the leakage of the residual function. Okay. So, and I want to say, so first of all, this assumption eliminates the lower bound of of being able to compute the residual function, but it also eliminates the need for the correlated randomness or a dedicated party, which I had told you that all non-interactive protocols in the standard model do require. So we've really made a leap here. We've been able to do something that we cannot in a regular setting. But let's talk a little bit about the assumption. Bob, who's putting down the collateral, needs to make some assumption about the adversary's computing power. He says 1 million because he's assuming that the adversary can only expend 500,000. But there are a few things about that. First of all, Bob doesn't necessarily know the truth and can't really pin down the amount that it has to put down in order to prevent the computation of the residual function. It, of course, can take a margin of error. If it thinks that the adversary can spend 500,000, it could set the collateral at 5 million and go and get a loan and put that money down. But more than that, Bob is making sort of an assessment now at this point in time. And of course, over time, things might change about the abilities of the adversary. The adversary might become wealthy. You know, they invested in Algorand and they bought tokens, and now Algo is $10,000 and it can spend much more. So this is also some assumption that is being made about the financial capabilities of the adversary over time. So it's a complex assumption. Of course, if we could do it without, then great, but we cannot. So this is what we're taking, and we're doing it under this assumption. So you have to consider under which circumstances the assumption would hold. And for example, for ephemeral computations that will happen that are relevant for 10 minutes, then at least you don't have to consider the long range assumption about the abilities of the adversary. So when using this assumption, as with any other assumption, this is not specific to our assumption. One has to think in which cases does the assumption hold, and under those cases, assume that the protocol is secure. Okay. So now I'm going to go a little bit into our construction, and I'll in fact describe really only one piece of the construction, which luckily is the most elementary building block of the construction, because that's in fact where the zero knowledge proof is embedded. And given the workshop, I do want to talk about that. So we introduce a notion of Gage time capsules. And basically, what is a Gage time capsule? You commit to some value. By the way, if anybody has lost me up to now, you can join in here, because this really is starting a new thing, and you can join in and sort of keep on going with me. So what is this Gage time capsule? You take a value and you commit to this value, and you put some monetary collateral to say, yes, I will open this commitment in the future. And what do we know? Because it's Gage, as I told you for the other things, it is going to be designed in such a way that's going to enable miners to open the commitment in case I do not, if I'm the person committing. So we have this design that we want that says, if I am there, I will take back my collateral, and if not, we're ensured that somebody will open this commitment. This is different than regular commitments, which if you don't want to open and they're hard enough, nobody can open them. But this is going to be a commitment that it's going to be feasible for the miners to work and open the commitment. Same way that they do that, they find the appropriate hash for the next block in the blockchain. And so basically, what these Gage time capsules do is they bring the original time capsules from way back when into the blockchain and uses the monetary capabilities of the blockchain to open the capsule. So what's a time capsule? They were introduced in '96. Basically, Bob puts out a time capsule in which he hid some information. And Alice is gonna work over time, sort of chipping at it, trying to open the time capsule until she actually manages to open it and the value is exposed. So this is a time capsule. So here I'm gonna be a little bit technical, but not too heavy. So basically, what do we want to say about these time capsules? There's a commitment step that generates the commitment C, and D is going to be some value which enables the creator, if Bob creates the commitment, to open the commitment. Now, there are two security parameters in here. Lambda is the regular security parameter, which we all consider things to be hard, whatever it is. But lambda star is the thing that is sort of going to capture the complexity that it's going to take to brute force to open the time capsule. Think of it if you're thinking about the hashes for the blockchain and Bitcoin, it's sort of the missing bits that you need to find in order to find the correct hash that hashes to the value that you're looking for. And then we have decommitment verification. We're going to need this because people, you need, even if Bob is opening the time capsule, you need to know that it's actually the correct value, that this was the value that was committed to. And of course, we have the forced opening, which is the procedure which the miners are going to use to brute force open the time capsule. And we want, of course, binding and correctness, that you can't open it in two ways and prove this. But the most interesting property that we need, of course, is the hiding. The hiding, what does it mean when we're saying that actually it can be brute forced and opened? So this is something which we in fact define in our paper, which was missing in the original papers, really sort of the good definition of what it means. But I'm not going to mention it now, but whoever is interested can read it in our paper. But the idea is that we want to say it's going to take somebody 2 to the lambda star to open this thing, to give some indication of the work that it's going to require. And this should also, and as long as somebody works considerably less than that, they will not open the time capsule. And this is also true if you're trying to open a set of time capsules. We need this for our MPC setting. Even if you're trying to open kappa plus 1 and you work less than k times 2 to the lambda star, you won't open more than kappa capsules. I want to say, of course, and this we have to think when we talk about the adversary. Of course, the adversary could be bloody lucky, right? That in the construction, it's same thing when you're hashing for the blockchain, right? The first value that you choose might be the right one. And you can immediately open the capsule, which would be devastating for us with respect to the issue of computing the residual function. So we need to build our designs in such a way that this will not be an issue. And I'll point shortly when I get into the detailed design of how we're going to do this. Okay, so now we said that we're incorporating the opening of the time capsule into the blockchain. So I sat and worked And now I have to, I'm a miner. I want to receive the collateral that I had put down. I want to get that money. So now what do? I go and I say, okay, this is the opening of the time capsule. But somebody, some adversary is sitting. They're waiting for me to do this. They hear my response. They block my message. And they take and they post the response to the blockchain and they retrieve the collateral. So clearly, this is not sufficient in the most vanilla setting. We really need to create more sophisticated time capsules where you don't, in order to show that you've done the work, that you've brute forced the time capsule, you don't just post your opening to the blockchain. And here, of course, is where the zero knowledge is going to come in. What we need is time capsules that you can just prove that you know how to open them. And you want to bind this proof in such a way that even if someone copies it, it won't help them, because that proof is going to be meshed with the wallet into which the collateral needs to go in. This is going to be some tag in the zero knowledge proof. So the smart contract that we're going to use is going to utilize the tag inside the proof to know where to deliver the tokens to. So we see that it's really critical that we have the ability to do something in zero knowledge. And what's important here, I have to expose the message itself because that's needed for the computation. So I need to be able to prove that this message is the correct one, that I know it, and that it cannot be, that it will not be able to be copied even when I make the message public. So this means that the decommitment value needs to remain secret, despite the fact that the message itself is made public. Okay, so now we add a proof verification, and basically it takes the commitment, the message mu, which is what we claim is committed inside, the proof and the tag, and it outputs one if this is a correct commitment from the time capsule. Okay, so of course I could have stopped here. We can use any generic simulation sound extractable NISIC, include the tag in there for the incentivization, and we'd be done. But this would make things a little bit inefficient. I mean, such a generic proof would make our system, which we in fact also designed, information about the design built appears in the paper. We'd somewhat be missing the goal here because we really wanted to implement something that works. So what we did is we had a construction that worked, but we augmented it with some algebraic construction so that we could do an efficient zero knowledge proof. Okay, so don't get worried from this slide. I want to prove to you that that's the only bad slide in my thing. So the next one is already not like this. So if you want to not listen for a few minutes, you can. And when I move to the next slide, just come back in. So what is the construction of our time capsule? We choose a set of case seeds and we simply hash what we want to do is we want to give a witness to what's the seed that we used. We want to hash these seeds and XOR them into the message. And so the little commitments are for each one of these seeds, you have C1I, which takes the little seed and hashes it with H1. Then we create a K, which is a XOR of hashing all these seeds with HK. And then we simply do H2 of this K and we XOR it into the message. So how do you brute force it? You have to go and check all the C1I to see that you find the little SI. And these are set to a length that is possible to compute easily. And then you compute the other thing. Why it's comprised of K seeds, I will talk in a second, but that's not related here to the issue of the zero knowledge. It's really related to the issue of trying to defend against the leakage of the residual function. So in order to provide the zero knowledge proof, we add the portion, the algebraic portion, which is underneath the line, which gives you R, which is again some hash of these little seeds added together, and then we just commit to the R, G to the R, and H to the R, F of K, basically an El Gamal encryption of this value. And now it is easy to prove that we actually know R. K is given out in the clear, and you show that you know R just by doing this very standard proof that Muthu, I saw 4 minutes. Okay, this very standard proof. Okay, so now I just want to touch briefly on this very interesting point. This here, you see the part that's now sort of flashing, you see it? Why do we use multiple seeds? This goes back to the thing that I said, that the adversary could be extremely lucky and could just, in the first time that it guesses, it would guess the correct seed, and through that, really learn more information about the function. And we want to make that as small as possible. So this is the trick that enables us to do it. And if you're interested in it, then this all appears in the paper, including the analysis of why this construction really gives the probability that we want. So basically here you get this zero knowledge proof that enables a miner to present the fact that it has opened the time capsule and retrieve the collateral. And just to wrap things up about our construction to really get MPC, these proof of opening time capsules, those are the POTSIs. They're combined into a Gage time capsule, where really you open only one of the items. It gets an index J. You can see the index here, and only one is opened. And it can go to the right by having the committer retrieve its collateral, or the miners retrieve the collateral. Okay. And to finish the full construction, the multi-party computation uses garbled circuits. The Gage time capsules are used to commit to the labels. And then we also give two transformations. Everything is based on how much work you want the adversary to exert in order to get another value of the function. And as I said, this construction circumvents the lower bound of the leakage of the residual function. And in our paper, we give a specific example of how to run auctions with this mechanism, including the design. And now I'm gonna do a little plug-in. So at the foundation, that Algorand Foundation, we designed a questionnaire for people to self-report their COVID symptoms, if they have them or not. It's very, very important to report also if you don't. But the idea is here that it's a worldwide repository. Most apps that are out there focus on a specific location, but this is world round. And the most important and interesting fact about it is we de-anonymized the survey in such a way that the responses do not leak any information about, you cannot be identified through the answers of the survey. And through that, we're putting all the responses on the blockchain, which is great because this would enable people to do research going into the future, years from now. Everybody else who's collecting information, they store it locally and they do not share with other researchers. But this is going to be data that's going to be available to anybody who needs it 50 years from now when suddenly they want to do some research, or even next year if there's an outburst, to know more about what went on in this thing. So I highly encourage you to go to ireport-covid.app and submit your survey and share with your friends and help us make this a reality. So thank you very much.
Thanks, Tal. Really intriguing presentation. There are a few questions here, Tal. Let me, I'm just going to go through the chat and ask you these questions. I think we don't have too much time, so let me just start with a few.
Okay.
One of the first questions says, do you, I mean, the way I interpreted it maybe is that, do you tolerate rushing adversary? So the question is, do we require all messages XI to be announced at the same time, or they can depend on each other?
They can depend, that's fine. That's also true in any non-interactive setting. Somebody posts a message, others can wait to hear the answers. So, and I want to say something even more important. I didn't go into this because it's too many details, but the party who puts out the computation is in fact, is a unique party. And all the other parties' inputs can depend on that party's input, in fact. So we cannot compute if that party is collaborating with the adversary, it's not interesting. But anyway, despite the fact that it's not the pure vanilla definition of non-interactive multi-party computation, the lower bound still holds in this model. So there's a first party who puts out his input, and then everybody else's messages can depend on that, but still the lower bound holds. And yes, people can put the messages at any time.
Right. Then Markov here asks, does creating the collateral introduce an additional communication round?
No, putting in the collateral, no. That is non-interactive. But in fact, and this is a good point, of course, if you want to retrieve the collateral, you need to come in, and if you created it and you want to get it back, you need to come and announce what the information in the capsule was. And furthermore, also, if you don't do that, if you didn't come and retrieve the collateral, of course, the miners also have to announce what the input inside the time capsule was. But it's important to understand something about the miners. These miners, it could be anyone. It's not a dedicated set. As long as there are people who want to compute and receive money, this will happen. So you're not bound. You're saying, okay, these people are gone. These 5 people I was depending on to compute are gone. That's not an issue.
I had a question in between these things. Is there any relationship to optimistic fairness, like the way you're achieving this computation over here? Like there's this work of Ashokan et al. From a long time back where they involve a third party for in case someone drops out, but here you're using the miners and the blockchain to.
Of course, this also solves the problem of the fairness, because the output is always going to be revealed. The output of the function is always going to come out.
So Bezad Abdul Maleki asks, can the miners open the commitment to any value or just some valid message?
So this, of course, has to be one of the properties of the time capsule is that it can only be open to one, that you cannot open it to two values.
And I guess this is a comment here by Thomas Kerber. It says, how can we incentivize miners to not censor opening transactions? It seems like they have a vested interest to not allow these to go through to collect collateral.
Why do they have an incentive not to put things on the blockchain? I'm not 100% sure. Of course, if you have an adversary that's all powerful that can block every miner from posting to the blockchain, then you'd have a problem. But that's not a realistic model. And of course, this is exactly the point I was making before. There are people that are willing to mine all the time, right? They want to make money. So if there's an opportunity to make it, they'll want to make it. They don't care about this computation at all, what it is and so on. They know that there is this thing, they can mine it and they'll post the answer.
Alessandra,
Unless you misunderstood something in the question.
I think that's, unless if Thomas is there, I mean, maybe you have a follow-up?
Yes, so from my understanding, maybe I got this wrong, but my understanding was that the miners can claim the collateral if they open the commitment and the corresponding party hasn't opened it beforehand.
Yes.
And in that case, isn't it in the miner's interest to not allow the party to actually open their commitment so that they can claim these funds?
You know what? That's an interesting point. I agree, because there's, of course, but there's sort of this grace period when only the creator of the time capsule could post. But I can see your point that maybe is easier for the adversary only to only enable that to only block that thing. I have to think about this point.
There's another possible defense there, which is to make the collateral claiming transaction private so that the miners can't distinguish it from any other transaction. So if you have a private blockchain protocol anyway, then you could possibly do that.
Okay. Okay. I have to think about that. I am sure it can be somehow resolved, but I'll think about it a little bit more.
Dara, you had another question. Do you want to follow up with it directly?
Yeah, so in the case where the adversary for a forced opening has multiple capsules, you said that they can't open K capsules with less than K times 2 to the lambda star work.
They can't open more than kappa.
Okay, sorry, can't open more than kappa, yeah. Is that sufficient? Because they still potentially have an advantage in that they have a choice of K
okay.
capsules to open.
Okay.
Yeah.
Okay. So it's an excellent point. And in fact, the way that we build a construction, of course, if you're thinking about a Yao circuit, where there are n wires, even opening just one more label gives you information. It leaks information. Yeah. So you can say, okay, the adversary doesn't want to spend the $1 million. It'll spend $1,000 on one more label and it learned something. So in fact, I didn't speak about it, but it's an involved design of how the labels are connected together so that it's not sufficient for the adversary to exert only one more computation to get a little bit of additional information, even if not get a full another computation on a set of inputs. This you would need to look at the paper to see exactly how it's done.
Thank you. That answers the high level question.
We have time for one more question. It's from, I'm going to choose Alessandra Scafuro. Isn't there a problem with long-term hiding? Since everything is committed using time capsule, wouldn't all commitments open eventually?
Yes, exactly. So this is what I said when I spoke about, we have to understand what the assumption means and how long does it hold. So of course, over time, it degrades. And in fact, it degrades quite quickly in some sense. So you have to think, both when you're making the assumption, how much power does the adversary have now? How long do I want the information to be hidden? Make some assumption of how it's going to go into the future. And then set the collateral according to that. And most importantly, to think maybe for your application, it doesn't work. Maybe, but if you have a short-term thing that's ephemeral in some way, has to last 10 minutes, then you use it. But otherwise, definitely what you're saying is correct.
It will not be good for voting, for example. Voting will not be a good application.
It would not be a good application in that sense because you want votes. But auction, that we give an example of, is a great one, right? You put the thing, we use it for specific types of auctions. Of course, there are auctions where the information has to remain hidden. But if it's an auction that it's like zoom, zoom, zoom.
All right, so I think we're running a little over time. So there are more questions, Tal. I mean, later on, if you can, look at the chat to see who asked these questions. So let's all thank Tal. I'm going to clap on it.
I just see that Claire Nelson filled in the COVID-19 app. Thank you. And I'd be happy if all of you do too.
Yes, so everyone, please, go to this COVID-19 app and do it. I already did it a week back, so.
I'll put it here in the message so you can all